For next talk, we have Dr. Vijay Gadepally from MIT Lincoln Labs. A Lincoln Lab. I've been corrected on that before. He's going to be talking about the cool stuff that they've been doing with Accumulo. These guys were, I think, one of the first people to have documented use cases outside of government, which is kind of like a neat claim to fame. They are a little bit too smart, in my opinion, I think. They're doing some really, really cool advanced stuff with Accumulo that I don't think any of us really realized was possible. So we're really glad to have them, give a talk because it really shows what, how far you can take it. So I appreciate it. Here you go.
Well, thank you very much. So glad to be here today. Thank you in advance for listening to me. First of all, I'd like to thank the organizers of the Accumulo Summit. It's great to be able to meet a lot of the developers. We do a lot of work with Accumulo. We love it. So thank you all for being the developers, for developing this amazing technology that we can use for some advanced research. So today what I was going to talk to you about was a little bit of the work that we're doing at MIT Lincoln Labs, where Accumulo fits into that, and maybe some future directions for some of the advanced research that we do over there. Before I begin, though, a lot of the work that I'm presenting today is really joint work of quite a few individuals. So I wanted to make sure I acknowledge them before, especially because it's on video. So thank you all. All right. So I'll begin with a little bit of introduction about the lab itself for those who are not familiar. Sort of put everyone in perspective of what we look at as the cloud, because I think every one of us has a different definition of cloud data. We have our own definitions. And then talk to you about some of the R&D that we've been doing, and then what that's enabled us to do. So the Massachusetts Institute of Technology is a science and engineering institution in Cambridge, Massachusetts. They're really dedicated to research and education. Lincoln Laboratory, which is the largest lab at MIT, extends these goals of MIT for the purpose of national security, to develop technology for national security. So MIT Lincoln Laboratory is a DoD, federally funded research and development center, which is operated by MIT. And these are pictures of the two campuses. So MIT Lincoln Lab, again, the core purpose is really to develop technology that supports national security. We have a multitude of work areas. Chances are, if it's a technology, if it's something that we can tinker with, we're probably involved. And we work with quite a few different organizations across the government, industry, academia, in a variety of mission areas, again, with the purpose of trying to develop technology for national security. Lincoln Lab, again, has many hats. We not only work with developing technologies, building prototypes, but we have our own conferences, workshops. We have some pretty large conferences, in fact. We work very closely with universities across the United States. And we are also a trusted government advisor. So we work with folks when they have technology questions to guide them and provide them with information on directions to move in. So that's a little bit about MIT Lincoln Lab. And so I think this slide, everyone probably has their own version of this, but we all use this to sell products, to sell things. Essentially what we're trying to say here is that we have a lot of data and we really can't do much with it. The numbers here people may argue on, but the fact is that we have a lot more data than we can do things with. And typically these have been known as the 3 V's of big data. So volume, velocity, and variety. Volume's really dealing with the quantity of data, velocity with the speed that it's coming in, and variety with just the different types of data and how we can work with that. So we've got, at Lincoln Laboratory, we're really working with a large amount of different types of diverse data that's coming in at huge rates and at huge sizes. So this is the challenge that we work with. How do we take this data, process it in some way to be able to provide information to users who could be operators, analysts, folks on the front lines. So we want to give them answers fast. So working with many government organizations, we've developed what we call the Common Big Data Architecture. Now, a lot of these pieces probably look very familiar to you, and everyone has a version of this Common Big Data Architecture. And we found it very useful to just put names and labels on things. So every system has some data coming in. We're all here because of that. We've got some form of elastic computing that's connected to a scheduler. Now, this in some of these conferences, that's a debated thing, but take my word for it. We have some form of a scheduler. And then we're working with a file system. We have databases. We're trying to do some analytics. Eventually, we're providing some interface from this system to our users. right? So that could be queries from a database, analytics, whatever it may be. So kind of thinking of the 3 V's and the challenges that we have with the volume, velocity, and variety, Lincoln Laboratory has been developing technology that can be used to address some of these. So to address the problem of data volume, we found that access to a computing cloud is something that can help you deal with this vast quantities of data that you're bringing in. And the question of what type of cloud one wants to use is extremely dependent on the application you're in. So we've developed what we call the MIT SuperCloud, which is used to really combine different clouds. You will hear me use the word cloud a lot, so I'm sorry for all those who lost that in bingo already. To deal with the problem of data velocity, we use a high-performance database, and we've found nothing higher performance than Accumulo. So we love Accumulo. In fact, here are some results. This is a paper that has been accepted for a conference on which we show about 115 million entries per second as our ingest rate or insertion rate into a database. So we love that performance. And in order to work with the wide variety of data, because we believe this is where the answers lie, how do we correlate different pieces of information back to each other? We've developed what we call D4M, which is the dimensional distributed data model, which is a toolbox that can be used to deal with large quantities of data. And we've also created an interface with this to Apache Accumulo. So again, all that stuff in the middle is just the cloud. So these are all different technologies that we have to access the cloud, to work within pieces in the cloud. So what do we mean by cloud, right? So the cloud, depending on where you're from, I happen to come from a supercomputing background, so I'm used to simulations, and that's the cloud that I'm used to. Many here may be from the big data or the database cloud. There are many folks in the enterprise cloud as well. Each of these clouds typically have their own conferences. They've got their own multi-billion-dollar industries. And each cloud ecosystem that we've seen tends to use different hardware and software. They have different requirements. But to us, a cloud is just some racks of computers where we're able to process information quickly. So that's where we wanted MIT SuperCloud to sit. So we want the SuperCloud to be able to dynamically launch any of these clouds dependent on the application. So within the MIT SuperCloud, you could run a supercomputing job, so a high-performance computing job. For those that are familiar using a technology such as MPI, if you're in the database cloud and you're dealing with that type of transactions, you may want to launch a SQL cloud. We can do that as well. If you're in the big data community, you might want to do, of course, Apache Accumulo. Of course, we can do that. In the enterprise cloud, launching virtual machines. We don't want to, but we could run an Exchange server. We really don't want to. So that's really where MIT SuperCloud comes in. So that's our approach to dealing with the problem of data volume, is to create a cloud, but then to create a general enough cloud that you can deal with the different types of environments that you may need to set up. And some of the technologies that we make use of in this MIT SuperCloud, so for the supercomputing community, we have high-performance scientific computing. We have technologies like MPI, OpenMP. In the database community, we have SQL, different flavors of SQL. Big data, we work extensively with Hadoop, D4M, which is our interface to Accumulo, and of course, Accumulo. And in the enterprise, VMware, and we're investigating new technologies in that space as well. So the MIT SuperCloud essentially was developed to address the challenge of big data volume. It allows different ecosystems, so different cloud ecosystems, to coexist in the same place. So we're using the same hardware for running these different types of systems. And we've seen extremely high performance in each of these systems. And we're able to keep some of the main benefits that these ecosystems provide. So some of the innovations that we had were really in being able to take high-performance computing systems and share that amongst other forms of computing that may be needed. Of course, we are a high-performance group, and because our mission is to develop technology for national security, must be reliable. So we've really brought the power of cloud computing to the HPC community. And you'll see that in my talk today when I'm talking about some of the research, is really about how we get the research community to make use of some of this advanced technology in databases and big data. So just a picture of where MIT SuperCloud sits in between all these technologies. At any given time, we have all these clouds operating simultaneously. So we can run a high-performance computing job against Accumulo. We can do run that against SQL. really the possibilities are endless. And we find that flexibility extremely useful. So like I said, so TXE1 is one of our clusters that we have at Lincoln Laboratory, which is in Holyoke, Massachusetts. At any given time in our cluster, we can run different types of jobs: MATLAB, VMware, Hadoop, big data, Accumulo, whatever it may be. So one of the big pieces of MIT SuperCloud, and if we remember the cloud diagram from before, was the need for a high-performance database, because at least a couple of those mission areas require access to data very quickly. So the centerpiece of this is really the Accumulo database. So I guess I don't need to tell people too much about Apache Accumulo, but we have validated that it is the highest performance database that we've been able to see, at least open source database. It was contributed to the Apache project in 2011, and it's used extensively in government, private, and research for research applications. One of the key requirements for this is to develop some form of a schema, and I'll talk to you about the schema that we've developed at Lincoln Laboratory in conjunction with many folks in the government. And again, we are a high-performance computing group. We work extensively in benchmarking and performance testing. So this is sort of our, we had, in 2012, we released some numbers, which we were doing about 4 million entries per second insertion into Accumulo. We are now able to go to about 115 million entries per second on only about 200 nodes. So which is extremely fast, and we've not seen any published numbers that are this high with this amount of hardware. So Accumulo is high performance. Why do we love Accumulo? We love that it's open source, so we can transition this to people when they want to use it. We love that security is baked in, and the presentation before this is just proof of that it's come with security from the beginning. It's not just an afterthought that people have put in, oh, we need security, okay. But it comes with that inbuilt, which is something we love. Of course, it's high performance. It's widely adopted. We've got, you can see quite a few people here. And it's got a great developer community. So we've had a lot of luck with working with folks in the Accumulo community to learn about what's happening next and to even maybe play some part in future directions of Accumulo. One of the challenges that we found with Accumulo was bringing this technology to the research community. So Lincoln Laboratory has a large number of signal processing engineers. For those who may have long forgotten that, we're dealing with Fourier transforms and Laplace transforms. We've got a lot of people that do that. And then we're talking to them about databases. So there's a divide. So in order to help close that gap, we've worked on a tool called D4M, which helps researchers use Accumulo for their research. And we've seen a lot of success with that. So just kind of bringing this back to our common big data architecture, we use Accumulo as a solution for our data velocity problem. And we've seen great results with doing that. So Accumulo plays a key piece of the work that we do at MIT Lincoln Labs. So the high-level language is called D4M, which actually contains many different features. So it extends mathematical operations. It's actually written in we have a lot of mathematical theory behind the work that we're doing. So we've actually proved, what type of fields data lies in. Because of the mathematical foundation, we're able to connect with graph algorithms, which is another huge research area for us. One of the so we have, the math. We have the ability to perform operations on math. So we're able to add two pieces of big data, and actually have a mathematical definition for what that means. So you could add two tweets together, which is always fun. We can also connect this to an Accumulo database. So having that connector to a database is another important piece of this technology. So we've been working extensively on trying to figure out the relationship between linear algebra, signal processing, and big data. And we've actually gotten a lot of results, and I'm happy to, I decided not to bore people with those details here, but if you are that type of person who enjoys it, please find me after. I'll be more than happy to give you the gory details of how big data and linear algebra are connected. So D4M takes associative arrays, the concept of associative arrays, binds them to databases, and allows rapid prototyping of data-intensive applications. It supports database and computational systems that deal with big data. It was developed at Lincoln Laboratory. It is now used extensively by many folks outside of the lab as well. Associate arrays are a key concept which form the data and mathematical foundation for the work. We have a data schema that relates back to associate arrays, and we have a low barrier to entry for signal processing engineers who work in familiar languages like MATLAB or Octave. We have an API that's accessible to them. So how many people here are MATLAB or Octave users? All right, that is 4 more than I thought there would be. So, all right, so there are at least 4. So for those that have used that or are familiar with that, it is a technology, it is a programming language and environment used extensively by the engineering community. It's very good for quick prototyping of solutions. And it's a language that a lot of researchers at Lincoln Laboratory use. So the API is very accessible to them. The first piece are associate arrays. Associate arrays you can think of as a large sparse matrix. So a sparse matrix is a matrix where there are more places where there are no values than there are values. So think of it as something with a lot of zeros in it. So a large sparse matrix is, though, indexed by numbers. So you've got row 1, column 1, row 2, column 2. Associate arrays you can think of as a mathematical extension to that, using strings as the labeling for the rows and the columns. So if you look at the bottom left, chart on the bottom left, you could think of, let's say, 2 hashtags, A1 and B2, 2 tweets, and the existence of a point says that there was a tweet that contained both these hashtags in it. So in associate arrays, you can essentially take large pieces of data, label them by strings, and put them in some form of matrix representation, which kind of you'll see that relationship with linear algebra. So we're able to take, an example would be hashtag A1, hashtag B2 being a part of the same tweet. We also like this relationship that we have within associate arrays to a triple store database. So you could think of your row, column, and your value as being a triple that you could then store in a database. We're able to do mathematical operations, so I could add 2 associate arrays together, and that's defined. There is a defined outcome for that. We can use array indexing, so if I wanted to find everything from hashtag A1 to hashtag B2, give me all the other information. Otherwise, I could do that as well. I could look for equality. And because we work with a lot of signal processing folks who work in advanced graph algorithms, there is a one-to-one relationship between the associate array and its representation in a graph. And a graph is essentially a representation in which we have nodes and edges, or vertices and edges, and an edge connecting 2 vertices. So essentially that green line over there shows a connection between 2 vertices. And we can define what we mean by this connection in many different ways. In this example over here, we're saying that an edge, the existence of an edge between 2 vertices, means that they're connected by the same tweet. So it's great that you can have this go back and forth. There are many great algorithms that people have developed for working on graphs, which being able to perform linear algebra. So if you wanted to do, how many here are familiar with breadth first search? So it's a very common graph algorithm. That's essentially a multiplication. So you're just essentially it's a multiplication of 2 associate arrays. So it's a very quick, it's a nice parallel. It's a very common algorithm, and it's very easy for us to do that with this one-to-one representation with associate arrays. The second piece of what we did with D4M was really in developing a data schema. So the schema is really about how do we organize data, how do we take the semantic information that comes to us in maybe from different types of sensors and organize them in a common format. So we have looked at looking at the associate array representation. We've looked at the schema that we've developed uses a 3-tuple to represent all pieces of data, and this schema is known as the new wave or the D4M schema, which some of you may have heard of outside. So essentially what we're doing is, if we go to the previous slide, we're taking our row, our column, and our value, and that's how we store our data in the triple. So we have a row, column, and a value. Now you should see that this sounds very familiar, or very close to what the Accumulo data schema is like. So we've kind of simplified the Accumulo data schema to really have 3 pieces, because that's what, at the end, the researchers really wanted to quickly access data and not maybe get caught up on some of the other finer-grained implementations of it. So we use a 4-table representation, and these 4 tables are able to completely represent almost any piece of data that we've been looking at. So just as an example over here with the cool animation, if we had a raw data coming in, this could be computer log files, could be social media, could be anything. we can, using one table, take the row values and we create row labels, which is essentially a value or the label appended by a value. And to create unique columns, we can take the column and append the value of the column. So if we had a column called column 1 and a value called row 1, column 1, we'd have a new column called column 1, and we use a pipe separator, and then column 1, row 1. And we can do this for our entire data set. So we'll have these large sparse arrays. Now looking at some of the properties of Accumulo, why we chose this design is row lookups are fast, so we can look for data in a row very quickly, and adding new columns is cheap. So we can create large amounts of columns and we can look up rows very quickly. But we realized if we just have this one table at the top, we still may, more often than not, we want to look at a value for, this is a column. Tell me where my destination IP address was 128.0.0.1. So we'd have to do a full scan of the column. So we've actually stored, and this is a common linear algebra trick, the transpose of the matrix. And a transpose is essentially take a matrix and just tip it over, right? So your rows become your columns and your columns become your rows. So if we want to look up a column really quickly, we go to the transpose table, which is at the bottom, and we can look up a column just as fast. And D4M seamlessly deals with, depending on what you're asking for, it will figure out whether you're looking for the column or you're looking at the row. And this is really at the cost of storing our data 2 times. We've not run into too many problems with physical space for data, so the solution has been okay for us. We also store what we call a degree table, which is essentially a summation. So we take our columns and collapse them and count the number of times that a particular column exists. This is extremely helpful for query planning. So if I'm looking for, I have to use them again. If I'm looking for Justin Bieber in Washington, D.C., I might find that there are more tweets about Bieber, so I'll first look for things about D.C., then I'll look for things within that about Bieber. I would never actually do that, but if one wants to, you can. You are more than welcome to. And we also store the text table, which is essentially a way to keep the original information intact. We found with social media, sometimes you just want the tweet. You just want the original tweet. You don't just want the word out of it. So we've been able to, so there's this one-to-one relationship using this schema. So we have a row, a column, and a value. So this is our triple store database. So D4M, and this is an associate array. This is what we store in Accumulo. This is what we store in the file system. And this is how we can do a graph algorithm. So we found this extremely useful, this representation of our data. So I think I'm running low on time, so I will move a little bit faster. But this has all been implemented. We have about 3,500 lines of programming in MATLAB. The reason we wanted to work with MATLAB is, of course, we've got a large user base. It also has a first-class support for two-dimensional arrays. So when we're trying to define multiplication between associative arrays, we can actually do that. And it also has great support for sparse linear algebra, which is where we took a lot of the cues for what we were doing. And we've seen on some applications that we've seen, it's about 50 times less effort than Java or SQL for some of the operations. So if I'm trying to do a graph traversal, that's many, many lines of code in SQL. And we've actually tried writing it. And it's a multiply in this. So it's 1 line of code here because of this representation, because of the linear algebra support. And we also have some high-performance parallel implementations of this as well, because we always try for we are always going for high performance. That's what we're trained to do. So we found that D4M schema is really helpful with data variety. So I could give you an intelligence report, I could give you social media analysis, and you could put it all into the same table using the same schema for organization. So that's something that we found extremely useful. And very often we are trying to correlate different types of data with each other. And that's something of great importance to us and our sponsors. So I finally wanted to talk to you. So this is technology that we've developed. And we are using this extensively, and you can download this. Talk to me if you're interested in learning more. I'd be happy to talk to you about that. But I want to talk to you about what this enables us to do, right? Because that's really what's more important than, OK, it's great that you have this, but what can you do with it? So in the time that I have remaining, I want to talk to you about some of the projects. And this is just a subset of the projects that we have ongoing that use these technologies. The first is what I like to call supporting national security through rapid solution prototyping. So this is an example of, this is all the lines of code that one would need to do for the analytic. I'll tell you what it is. So there was a tornado in 2013 in Moore, Oklahoma. It was a very large tornado. And people had a Twitter hashtag that they used called #PrayForOklahoma, which is really used for people to show their support for the victims and the people in Moore, Oklahoma. And for many people here, this is probably an analytic that you'd want to do. Find where something is and plot it on a map. It's 3 lines of code here. And again, these are code that you could use for something completely different. If I wanted to do server IPs, find out where a particular IP address was used, it would be the 3 lines of code, except I'd change the hashtag to the IP. Yes?
How is it to integrate this kind of thing into a web application? Are there the hooks?
So we're working on the hooks. We're not there yet, but this is definitely within the goal of what we want to do. So we could, for example, so this is written to a KML file, which is read into Google Earth. You could have something that goes to Google Maps as well. They've got an open API that you can use for that. We've also been looking at other technologies that are out there. I know for my dissertation and stuff like that, I used OpenStreetMap extensively. So for putting things on a map, we have many choices. We kind of chose KML because it's a quick way, and there are a lot of people who make use of that. But this is, so what we've done here is we've done one query to find out every tweet with a #PrayForOklahoma. Then I want to find everything within a particular latitude, longitude range, and this is near Moore, Oklahoma. And then I want to plot everything. So 3 lines of code to do that. So we believe that this is extremely powerful in right after a natural disaster, right after something happens, you can quickly look at, within a few lines of code, you can prototype a solution for an analytic that you're looking at. And this is where the high-level language is extremely helpful. And again, this is all using Accumulo, and we have to have Accumulo on the back end to deal with the type of data rates that we're working with. And yeah, this is the graph and the associated array representation for the graph. So we took the raw data, put it into a graph form, and then able to plot that. The next is what we're trying to develop called domain agnostic analytics. So I'm a signal processing person. Many of the people I work with are also signal processing people. About 20, 30 years ago, we're kind of where we were with big data. You'd see a signal, you'd have this very one-off solution that would work with that signal. There was a lot of theory, but people were developing, I can do this one thing, right? I can take your signal and do this cool thing with this one thing, only with that signal and only this one thing. And we feel like there's a lot of that going around in the data community as well, where there's a lot of, we can only work with certain types of data. So we've been looking at how we can extend some of the signal processing work and look at the parallels that has in the big data community to develop these domain agnostic analytics. So I should be able to perform some analysis on a data set, regardless of if it's social media, intelligence reports, weather reports. I should be able to get some understanding. Of course, you're going to need domain knowledge to go further, but there should be a baseline of information that you can get just looking at your data set. So an example of that is big data filtering and sampling. And I have to use our friend again, Justin Bieber. Very often, people that we work with do not care about tweets that came from popular users like Justin Bieber, Taylor Swift, other people like that. So is there a way to filter these out? Is there a way to get rid of this information? Because we're inundating our systems with this large amounts of information. Very often, if you look at the statistical distribution of data as it comes in, it follows what's called a power law distribution. It's also known as the Pareto principle, the 80-20 rule. Think wealth inequality. It's essentially, there are very few people with a lot of money and a lot of people with no money. There are a lot of Twitter users with a lot of tweets or followers and many users that have no followers or tweets. So very often we're trying to get rid of the most popular information because if you think of, let's say an intelligence application, maybe you're not trying to look for these very popular, but you're looking for the needle in a haystack. So you're inundating your system with these very popular users, and you're not getting any data from it. You're not getting your analytics. If you're trying to do machine learning algorithms, you're training on the wrong types of information. So we've been looking at how can we do filtering, regardless of so you may need to know, you might have to have information on the domain to figure out where your filter cutoffs are. But the concept of filtering can be done agnostic of the domain that you're working in. Another research area that we have in this is background removal, so removing background noise. An example that we use very often is if you look at network logs, people go to google.com a lot. Apparently, we have lots of questions, right? And again, maybe that's not what your analytic is looking for. Maybe your analytic is not looking for google.com, but it's a person visiting that finest in spyware website on the internet. Right? Maybe that's what you're looking for. So if we have a signal and noise, we can think of this background as noise in the sense of data. So if we can, in using associative array terminology, subtract off the noise, it's a nice little symbol. Signal and noise minus noise equals signal. So the idea is to get this residual data which contains the signal of interest. So we're taking away some of the data that is background or maybe that we're not interested in. Big data also gives us the ability to pick what we mean by noise, right? So we can choose noise based on criteria that we have. So maybe in a network log situation, that noise might be the most popular nodes. So I want to remove that. Maybe in a social media application, I mean something completely different by noise. So it gives us that flexibility. And all this kind of comes back down to our looking for subgraphs, being able to represent big data as graphs, and do analytics on these graphs. Now, the next project that I'd like to briefly talk about is what we call the Lincoln Secure and Resilient Cloud, which is an ongoing research effort in which we're looking at how we can secure different components of the cloud. And this is where the Accumulo security inbuilt is extremely helpful for us. So we kind of looked at what are the operations that occur in a cloud. You've got some form of communication, you're storing data, you're processing data, and you have an underlying architecture on top of which everything is built. So we're trying to secure all these pieces. So what we're looking at is technologies that we can use to secure our communication and provenance. That actually has Accumulo as a part of it. Secure and resilient storage, of course, Accumulo is a large part of that. And secure and resilient processing. So how can I actually perform analytics securely? And on top of all this, we want to secure our architecture itself. And finally, I want to talk to you about one of these instances of securing our analytics that we've developed. And it's called computing en masse data. And this is really to ensure privacy of data. So I probably don't need to tell everyone here, but there are a lot of challenges. And this is just all I could fit that was somewhat readable by the first 4 rows. There are many, many, many challenges with big data, cloud, security, etc. There are many approaches to this. We found that the best approach so far is really you encrypt data at rest, and when it's in flight, you pray to God. So that's sort of the best case scenario right now. But we think that the vision is really that I have a sensor. It encrypts when the data comes out of it, as close to the sensor as possible. And the only time it's decrypted is when the user actually uses it. Right? So everything that occurs within the cloud, let that be the computing. So if I'm trying to add 2 things together or multiply 2 things, we want that to happen on encrypted data. If we're storing things, we want that to be encrypted. We want data that's moving around to be encrypted. Just encrypted all the time. And it's only decrypted eventually by the user. Now that's a challenge that is a lot of active research going on, not just at the laboratory, but outside of the laboratory. Many companies, universities that are working on this. And they have come up with solutions for this. Some of these solutions are somewhat computationally infeasible for the type of work that we do. Right? We cannot deal with the overhead of 10 to the power of 7. So imagine doing 1 multiplication is equivalent to 10 million multiplications. So if you have an application that has 10 million multiplications, that's 10 to the 14 multiplications. I'm not even sure what that number is. So it's a lot. So we've been working on what we call computing en masse data, in which we're able to have data that's masked. And we use the term masked because we're using a slightly weaker form of encryption. So data that's masked and is stored in an Accumulo database masked. And we can do queries on this data, all while the data is masked throughout the process. The only time it's finally unmasked is when it reaches the end user. So if I'm now embarrassed to look for Justin Bieber in Washington, D.C., I can look for masked versions of that. So my cloud operator does not know how pathetic I guess I would be in that case. Again, to talk to you about some of the simplicity. So we take the same representation for the data that I talked about before, the new wave or the D4M schema. We can use a mask command to mask this using some password or passcode that you have. And you can use a put to put it into your database. If I want to look for it, and of course I've got my friend there, it's two queries. One query to get the main table's data back, and another query to get the text table's data back. And I can unmask these results. So in this entire process, the data was masked when it left my system. It was stored remotely in a masked form, and it came back to me masked, and I only unmasked it back on my local system. This is a very active area of research for us, and we're working on improving the implementation that we have in this. So I think with that, I'm almost done. So in summary, we work with a lot of data. We do a lot of things with this data. Some of the key pieces, again, and I cannot thank you enough for helping develop this Apache Accumulo, because we make use of it a lot. And we're always interested in technical exchange with the big data community. With that, I guess if there are any questions, I'd be happy to answer them. Yes, sir.
So for the encrypted database, you're talking about when you don't trust the cloud,
Mm-hmm.
some sort of homomorphic encryption?
So homomorphic, so let me just repeat the question for the camera. Yeah. So the question is, what is the type of encryption that we're using on the cloud? So currently, we're making use of deterministic encryption, which is an encryption form in which the plain text and the ciphertext, for a given plain text and key passcode or a password, you will have the same ciphertext. And the ciphertext is the encrypted version of a data set. So with that, we can perform queries on a database. So if I encrypted a word today using a certain passcode, I would end up with the same ciphertext. So I could now query for that ciphertext in a database. Fully homomorphic encryption is a wonderful technology which would really get us to the vision on the right side. But unfortunately, right now, and this is a very active area of research, homomorphic encryption has high performance overhead associated with it. So and I have a friend over here who works is in part of the cryptography team, is look at other types of securing data as it's moving around in the cloud. And there are other forms of this, such as multi-party computation.
But the ultimate thing, you don't want to use access control because you don't trust the cloud infrastructure?
Yes. Well, we want the cloud infrastructure to not contain data that could be compromised. Or we want it to be stored securely enough that even if the data was compromised in some way, that they would not have access to the contents of the information. So if they got access to ciphertext, we'd want it to be a strong enough form of encryption that was used for that access to the ciphertext would not give them much information about the actual data in there.
But without the homomorphic encryption, you're not going to be able to actually do computation in that untrustworthy cloud.
So there are other strategies for that. So currently we're working on using different types of encryption that give us some level of functionality. So the computation could be querying, so looking for matches. It could be looking for ranges. And we're actually able to perform some computation on the encrypted data itself. So for example, an associative array multiply, we can do that on encrypted data itself. And the result when we're decrypting will actually get the original result that we were looking for, because we're making use of deterministic encryption on that. So we can perform some computation, but yes, I agree, fully homomorphic encryption is sort of the dream. It is, where we could actually have that vision completely satisfied and have an extremely secure version of encryption. So the question is, so the question is, we're really concerned, we should be concerned about data when it's sitting somewhere that somebody has access to, but maybe not at other pieces. So maybe the processing part of it wouldn't be as important. And that's really where we are today, but there are ways to actually read data in other stages within the pipeline. So you could, if data was in your RAM, you could actually get access to it. I mean, it would be a very determined individual or group of people, but you could have access to that. So the idea is to keep it encrypted for ideally the entire process, but at least as close to the entire process as possible. So, okay. If there are any other questions, I'll be hanging out. Please feel free to ask me. Thank you again. Have a great day.